Please pause the video and try the problem. And now let's discuss the problem. Here's a summary of the solution. Let's go through the solution step by step. When possible, represent what the question is asking you for with a symbol. The question asks, how long does it take the box to reach the bottom of the ramp? So the question is asking us for the time that elapses between this initial point and this final point. The symbol for time elapsed is delta t. The problem tells us that the box is moving down the ramp. So we draw the velocity vector pointing parallel to and down the ramp. The problem uses units of kilograms and meters, which are both SI units. The problem refers to concepts of mass and friction, which fit into the Newton's second law framework. The problem also mentions concepts of height, a type of distance, and time elapsed. Those concepts fit into the kinematics framework. So we expect to apply both kinematics and Newton's second law for this problem. We say that it's general kinematics to emphasize that we're not applying projectile motion. And we say that it's one-dimensional kinematics because the box will be moving in a straight line. The connecting link between kinematics and Newton's second law is acceleration. If we choose these axes, then the box will be moving in the x component. So we expect to apply kinematics to the x component, so the connecting link will be a sub x. The problem is asking us for time elapsed, which is a kinematics variable. So our plan for this problem is to use Newton's second law to determine a sub x. Then we substitute our result for a sub x into the general one-dimensional kinematics framework. Then we use kinematics to determine delta t. As I mentioned in the previous video, my personal preference for this type of problem is to set up both frameworks before using the frameworks to solve the problem. And my preference is to begin by setting up the Newton's second law framework. We begin the setup for Newton's second law by drawing the free body diagram. The problem mentions the mass of the box, and that's a clue that our free body diagram should focus on the box. The box is being touched by the surface of the ramp, which will exert a normal force and a frictional force on the box. The box is sliding across the ramp, so we apply kinetic friction. We use these rules to determine the directions of the forces. Now, we work on the force table. The box is moving parallel to and down the ramp. So I'll choose a positive x direction that's pointing parallel to and down the ramp. We use this rule to break the normal force and the kinetic friction force into components. The weight force is neither parallel nor anti-parallel to either of our axes for this problem, so we will not use this rule to break the weight force into components. We need to use the SOHCAHTOA approach for the weight force. Here's a summary of the process for breaking the weight force into components. I explained the process for breaking the weight force into components for an inclined plane problem in detail in an earlier video in this series. For this problem, be sure to include this negative sign on w sub y. Remember, we used this rule to determine the correct directions for the components. Now let's set up our Newton's second law equations. The box is moving parallel to the ramp in the x component. The box has no motion perpendicular to the ramp. The box is motionless in the y component, so we can substitute 0 for a sub y. Now that we've finished setting up our Newton's second law equations, I think this is a good point in our solution to shift gears and set up our kinematics problem-solving framework. There are two different types of kinematics that we could apply in an introductory course: constant velocity or constant acceleration with changing velocity. So let's decide which applies for this problem. The problem says that the box starts sliding down the ramp. That wording implies that the box starts sliding from rest. Well, if it begins from rest and begins sliding, that tells us that the velocity is changing. So we know that we are not dealing with constant velocity. What about the acceleration? Well, the forces on the box are constant. That means that the net force on the box is constant, and according to Newton's second law, that means that the box's acceleration is constant. So for this problem, we will apply constant acceleration with changing velocity kinematics. For a kinematics problem, we should try to build as much kinematics information as possible into our sketch. We can indicate that the box's path of motion is from this point to this point just by drawing this arrow on the path. We can label the key points in time t sub 0 when the box starts sliding at the top of the ramp, and t sub 1 when the box reaches the bottom of the ramp. As usual, it's conventional to set t sub 0 equal to the number 0. Most general one-dimensional kinematics problems will involve an object that either begins or ends at rest. This problem tells us that the box starts sliding. That wording implies that the box starts sliding from rest. So we can say that the x component of the velocity at time 0 is 0, and we can build that information into our sketch. Notice that the box is moving in the x component, so we're planning to apply kinematics to the x component, so I wrote down this kinematics variable specifically for the x component. Let's choose t sub 0 and t sub 1 as our initial and final points, and label those as I and f. The initial and final points are the points that we are going to substitute into our kinematics equation. When possible, represent what the question is asking you for with a symbol. We've seen that we can represent what this question is asking us for with the symbol delta t. When possible, build the question into your sketch. For this problem, we can build the question into the sketch like so. Here, we've indicated that the question is asking us for the time that elapses between this initial point and this final point. When possible, build the question into your sketch. Now we're ready to work with our kinematics setup. Remember that the kinematics setup begins by simply listing the general symbols for the 5 kinematics variables. In your kinematics setup, label the variable the question is asking you for with a question mark. We've seen that this question is asking us for the kinematics variable delta t. So in our setup, we label the variable delta t with a question mark. We'll see momentarily why this label is useful. Next, we continue our kinematics setup by listing these specific numbers or symbols that we're going to be using for the kinematics variables for this particular problem. So far, we don't have anything more specific to use for delta t, so we continue to use the symbol delta t. We have already decided that the initial velocity is 0, so I'll indicate that v initial x is 0. Remember that when the problem says that the box starts sliding down the ramp, that wording implies that the box begins its motion from rest. We've decided that our final point in time is time 1. So for v final x, we can use this slightly more specific symbol, v sub 1x. And so far for a sub x, we have nothing more specific to use than the symbol a sub x. Remember that we expect to use a sub x as our connecting link between our kinematics framework and our Newton's second law framework. Now we have to do some work to determine delta x. We need to begin by determining what distance in our sketch represents delta x. Well, what does delta x stand for? Delta x stands for the x component of the displacement between our initial point and our final point. The object is being displaced from this initial point to this final point. So the object is being displaced from here to here. So this arrow that I've highlighted in color represents the box's displacement between the initial point and the final point. Now we've chosen an x-axis that is parallel to the ramp. So this colored arrow also represents the x component of the displacement. Build as much kinematics information as you can into your sketch. You can see that I've built the symbol delta x into my sketch to indicate that this colored arrow from here to here represents delta x, the x component of the displacement. Now the problem gave us that we were dealing with a height of 5 meters. But notice that we can now see that that distance of 5 meters does not represent delta x. The 5 meters represents the vertical distance from here to here. But the object is not being displaced vertically, the object is being displaced parallel to the ramp. I've been encouraging you to label the initial and final points on the path with the symbols I and F, and I think that habit would pay off for this problem. That allows us to more clearly see that this 5 meter vertical distance does not represent the displacement. So now we have to use SOHCAHTOA, which will allow us to use this 5 meter distance and this angle that we were given to determine delta x. Actually, let's first determine whether delta x is positive or negative. Remember that the symbol delta x stands specifically for the x component of the displacement. Well, the box is being displaced parallel to and down the ramp. That represents our positive x direction, so we can say that delta x will be positive. We've determined that delta x will be positive. Now let's go through the SOHCAHTOA process to determine the magnitude of delta x. First, we have to decide which angle in the right triangle we're going to focus on. So I've drawn an asterisk here to indicate that we're going to focus on this 35-degree angle that we were given. I label this side as the hypotenuse because it's across from the 90-degree angle. I label this leg as adjacent because it's adjacent to the 35-degree angle which we've chosen to focus on. And I label this leg as opposite because it's opposite to the 35-degree angle which we've chosen to focus on. Now, should we apply sine, cosine, or tangent? Well, we need an equation that involves the length of the opposite side, so that we'll be able to substitute our number of 5 meters into the equation. And we need an equation that involves the hypotenuse, because that represents delta x, which is what we're trying to figure out. So we need to use the trigonometric function that involves the opposite side and the hypotenuse. That's the sine. So, sine is opposite over hypotenuse. For the length of the opposite side, we substitute 5 meters. The length of the hypotenuse represents the magnitude of delta x. We need to solve this equation for delta x. The first step in that process is to get delta x out of the denominator of this fraction. And we can do that by multiplying both sides of the equation by delta x. So now our new equation looks like this, and you can see that now we've succeeded at moving delta x out of the denominator of that fraction. Now we need to get delta x by itself by dividing both sides of the equation by the sine of 35 degrees. Then we do this calculation, 5 divided by the sine of 35 degrees, which gives us that the magnitude of delta x is 8.7 meters. Now, remember that we use absolute value symbols in our SOHCAHTOA equations to remind ourselves that the SOHCAHTOA equations can only tell us the magnitudes of the component. It's our job to determine the sign of a component in a separate step. Well, we already determined that the object was being displaced in the positive direction. So now in this last step, we can say that delta x will be positive 8.7 meters. Remember, it's a good habit to include a plus sign in front of a positive component because that will help you to notice when you need a negative sign in front of a negative component. Remember that we should build as much information as possible into the sketch. So let's build this number we determined for delta x into our sketch. So now I've built our numerical result for delta x into the sketch. We should also take our result for delta x and build it into our kinematics setup. Notice that for this problem, we had to apply the SOHCAHTOA process twice. First, we applied the SOHCAHTOA process in order to break the weight force into components. Then, separately, we applied the SOHCAHTOA process again in order to determine delta x. And notice a very important difference in these two applications of SOHCAHTOA. In this application of SOHCAHTOA, we multiplied a number by the sine of 35 degrees in order to get our result. But in this application of SOHCAHTOA, we divided a number by the sine of 35 degrees in order to get a result. The moral is that when you're applying SOHCAHTOA, you should not assume that you will be multiplying or dividing by sine or cosine. Instead, you should use the SOHCAHTOA process to determine what the correct approach is for that particular application. Let me ask you a question. Were you able to successfully use SOHCAHTOA to determine the numerical value for delta x on this problem? If you were able to determine delta x, excellent. That shows that you've made good progress at using the SOHCAHTOA process. On the other hand, if you were not able to determine delta x, that indicates that you still need to put in some more practice. Keep in mind that I have an entire video series about the SOHCAHTOA process. I'll put a link to that video series in the video description box. Now that we've completed our kinematic setup, and we've also completed our Newton's second law setup, we're ready to do further work with our 3 columns. Which of these 3 columns should we work with first? For the kinematics column, it helps to count the number of knowns. When you know values for 3 kinematics variables, that's when you're ready to choose a kinematics equation. Well, so far we only know values for 2 of the kinematics variables, so we're not ready yet to choose a kinematics equation. In our Newton's second law equations, it's helpful to count the number of unknowns rather than the number of knowns. In our Newton's second law x equation, we still have 2 unknowns, so we're not ready yet to do further work with the Newton's second law x equation. In our Newton's second law y equation, we only have 1 unknown, n. So now would be a good time to solve the Newton's second law y equation for n. And we discover that n equals 64.2 newtons. Now we can substitute our value for n into the Newton's second law x equation. Now we still know only 2 of the kinematics variables, so we're still not ready to choose a kinematics equation. But at this point, there's only 1 unknown in the Newton's second law x equation. So now we're ready to solve the Newton's second law x equation for a sub x. We get the result that a sub x equals positive 3.22 meters per second squared. Now we substitute our result for a sub x into our kinematics setup. Remember that our plan all along was to use a sub x as the connecting link between Newton's second law and kinematics. At this point, we now know values for 3 of the kinematics variables. And when we know values for 3 kinematics variables, that's when we're ready to choose a kinematics equation. The quickest way to choose a kinematics equation is to identify the kinematics variable which we do not care about. Well, we want an equation that involves delta x, v initial x, and a sub x because we know values for those variables. And we want the equation to include delta t because that's what the question is asking us for. That's why it's helpful to put a question mark above this variable. So the one kinematics variable which we do not particularly care about is v final x. Here is our list of kinematics equations for constant acceleration with changing velocity. We want the equation that is missing v final x. That's this equation. First, write down the general equation. Delta x equals v initial x delta t plus 1/2 a sub x delta t squared. Next, substitute specific numbers or symbols into the equation using the kinematics setup. For delta x, we substitute 8.7 meters. For v initial x, we substitute 0. For delta t, we continue to substitute delta t. For a sub x, we substitute 3.22 meters per second squared, as we determined over here. Our kinematics equation now has only one unknown, delta t. So we can now solve the equation for delta t. Our result is that delta t equals 2.32 seconds. We arrange our work in 3 adjacent columns to help keep our math organized. Now we're ready to answer the question. I'll round that answer off to 2.3 seconds. Check to make sure that you've included units with your answer. Make sure that you're answering the correct question For example, this question could have asked us about the final velocity. Let's check that our results make sense. It makes sense that this result came out to be positive because n stands for a magnitude, and magnitudes can never be negative. Our result for the size of n equals the magnitude of w sub y. And that makes sense because the normal force has to cancel w sub y to prevent w sub y from dragging the box into the surface of the ramp. Let's check whether our result for a sub x makes sense. Our result for a sub x is positive. Our positive x direction is parallel to and down the ramp. So a sub x points parallel to and down the ramp. A sub y is 0. So the overall acceleration points in the same direction as a sub x, parallel to and down the ramp. Does it make sense that the acceleration points down the ramp? Well, we know that in general, the direction of the acceleration vector does not indicate the object's direction of motion. But things are different if an object begins moving from rest. If an object begins moving from rest, then the direction of the acceleration does indicate what direction the object will begin moving. And this box did begin moving from rest. So if the acceleration is pointing parallel to and down the ramp, that tells us that from rest, the box must have begun moving parallel to and down the ramp. And that does make sense because we know that the box did begin moving down the ramp. So yes, it does make sense that the acceleration is pointing down the ramp. That's the only way the acceleration could point in order to explain why the box began moving down the ramp. The acceleration tells us how the velocity will change. If the velocity started at 0, the only way the velocity could change to point down the ramp is if the acceleration points down the ramp. Does it make sense that the magnitude of our result for a sub x is less than the magnitude of free fall acceleration? Yes, that does make sense. Because a sub x is being caused not by the full force of the weight, but only by w sub x. And furthermore, w sub x will be partially cancelled by the kinetic friction force. Now let's ask whether our result for delta t makes sense. This result came out to be about 2 seconds. So we can simply ask ourselves, in the real world, if we did this experiment of watching a box slide down a ramp from a height of 5 meters, would it seem reasonable if it took about 2 seconds for the box to slide down the ramp from a height of 5 meters? And I think, yeah, that seems approximately reasonable. Now, if you're from the United States, you might not have much everyday experience with units of meters. So in that case, it might be helpful to translate this height into yards or feet. If you have more everyday experience with yards and feet than you do with meters, then it would help to have memorized that 1 meter is roughly 1 yard, and 1 yard equals 3 feet. So 5 meters is roughly 5 yards, and the number of feet is 3 times the number of yards, so 5 yards is 15 feet. So this ramp is actually pretty high. The box is starting from a height of 15 feet. But I still think that it seems fairly reasonable that the box might be able to slide down the ramp from that height of 15 feet in about 2 seconds. Now let's do a recap of our work on this problem. This problem has a trap. The trap is this number 5 meters. The problem is trying to trick us into substituting the number 5 meters in for delta x in our kinematics equation. When we thought about it carefully, we saw that 5 meters does not represent the displacement on this problem. We had to use the number 5 meters to figure out the correct number for the displacement, and then we substituted that number into our kinematics equation. The moral is that on physics exams, you should not assume that a number that is given to you in the problem is the correct number to plug into your equations, even if the number has the appropriate units. 5 meters does have the right units to plug in for delta x. That's why it's a tempting trap, but it's still not the right number. You have to think about it and decide in each case whether a number is or is not the correct number to plug into your equations. If the number that's given in the problem is not the correct number to plug into your equations, then probably you need to use that given number to figure out the number that you should plug into your equations. Of course, even if you do notice that trap in the problem, that won't do you any good unless your SOHCAHTOA skills are strong enough so that you can actually use the 5 meters number and then apply SOHCAHTOA to figure out the correct number for delta x. So if that aspect of this problem gave you difficulty, you need to carefully study and practice the SOHCAHTOA method that we used for determining delta x. Remember that I have another video series that focuses just on learning and practicing SOHCAHTOA. You can find a link to that series in the video description box for this video. One of the keys to improving at SOHCAHTOA is simply writing down all the steps. Make a large, clean sketch. Build as much information as you can into the sketch. Notice how we noted what angle we're focusing on, and we labeled hypotenuse, opposite, and adjacent sides. And then, if you're having difficulty with SOHCAHTOA, write down each line of the SOHCAHTOA algebra, as I've demonstrated here. This problem illustrated, again, the usefulness of this simple kinematics setup. The simple kinematics setup consists of simply listing the 5 general kinematics variables and then listing the specific numbers or symbols that you will be using for those 5 variables. This simple kinematics setup helps us to organize the kinematics data. Remember that the wording of the problem implied that the object was beginning its motion from rest. That's how we knew that we could substitute 0 for v initial x. I think this is the first video in this series where we happen to use this particular kinematics equation. So make sure you understand the process that we took to deciding that this was the correct equation. We're ready to pick a kinematics equation when we know values for 3 of the kinematics variables. And we picked this equation because this equation is missing the one variable that we don't care about on this problem, v final x. I think it's important and useful that we labeled the variable that the question was asking us for with a question mark, because that helps to remind us that we do need an equation that involves delta t. Remember, this is the plan that we executed for solving this problem. On this problem, we used Newton's second law to find a sub x. Then we substituted our result for a sub x into the kinematics framework. Compare that with our plan for the previous problem in this series. In the previous problem, we used kinematics to find a sub x, then substituted our result for a sub x into the Newton's second law framework. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.